Well, good morning. We are going on with the examples for cable-stayed bridges, for special cable-stayed bridges. We looked into steel bridges and concrete bridges, and today we have a mix of both. We look into composite cable-stayed bridges. As usual, we look first into the general layout and then go into construction, which is our main interest because the theory we have covered in earlier lectures in the last semester. Now, we are talking about the bridge across the Houston Ship Channel at the small city of Baytown. We see here on the map, it's in the very south of the United States, and which is significant, it's very close to the Gulf of Mexico. Now, every year you hear in TV that there are major hurricanes coming through the Gulf of Mexico and making landfall somewhere in the south of the US. So the loading hurricane was an important factor in designing the bridge. We have here wind speeds up to 220 kilometers per hour. Just the general dimensions. We have a main span of 381 meters. Houston is the center of oil industry in Texas and in the United States. So there is a lot of very heavy truck traffic. There was until then, in the 1980s, a tunnel underneath the Houston Ship Channel, but that was too small for the heavy petrol traffic. So a bridge was decided upon. Since we are in Texas, where everything is bigger and better, it was decided we need 4 lanes in each direction, plus full shoulders, which if we combine these 2 directions in one beam, we come to over 50-meter widths. Now, using stay cables at the outside, we have cross girders with 50 meters, which is already a sizable small bridge. Consequently, when we did our first design with 2 cable planes, we found that the amount of steel required in the beam in the longitudinal direction for the main girders was in the same range as the steel required in the transverse direction, which is highly unusual. So we looked into other cable arrangements and finally settled for 2 separate beams with 2 cable planes each, meaning 4 cable planes. And then it turned out that the transverse steel was only 1/2 of the longitudinal steel required. Of course, the amount goes somewhere in with the square of the span. And later on it was proven that the 2 independent beams are aerodynamically more stable than any individual beam. So we decided not to connect them, again to save steel, because we were in a hard competition. Several years earlier, we also had a competition between concrete and steel alternate with Jean Muller in Tampa, Florida, Sunshine Skyway Bridge. And Jean Muller won because of approach bridges and things. So this time we said, we win, because he was again the competitor. And so we tried to make the bridge as efficient as possible, including the steel for the beam. Now, the towers then were a consequence of these 2 beams. We wanted 8 towers above deck for each beam for improved torsional stiffness. I told you about that. And then if we connect the two, we can also take the legs together to have only 2 foundations. And in this particular case, we have a full truss, meaning wind transversely goes in tension and compression only, no principal bending. Therefore, we could make it very, very slender. Again, we wanted to beat our competition. So this is the main layout. Main span 381 meters was given by the authorities, more or less by the conditions. Protection against ship collision is important. A lot of oil tankers going in and out the Houston Ship Channel. On one side, it was virtually founded on land, not reachable by the ships. And on the other side, in shallow water, we had a protective artificial island around the foundation. So again, if a ship would come into the direction near the tower, it would run into the artificial island. I said 2 separate beams were the most economic solution. And since we were given, so to say, the steel alternate, concrete was with the competition, Jean Muller, we said, okay, the good principles we had established for Sunshine Skyway, we use a steel grid with open sections, and we use as a deck, not an orthotropic deck, but concrete. Remember, no site welding in the United States, only bolting. So you cannot make boxes and things, these funny modern things. We don't do that in the US. We use open steel sections and bolt them together. Time on it, we've done it all the time, works very well. So then we, with a concrete deck, and there we considered cast in place or precast, we will see. Now, how to take, say, the horizontal loads over the length of the bridge, mainly braking, wind longitudinal. Well, the good thing normally is if originally, very often, the fixed point was here, and the beam was hung into one tower. That makes the towers unsymmetric, oversized that. And so we wanted to anchor it at both towers the same time so that horizontal forces are taken by both towers similarly. And what we chose here was we used rubber bearings 275 millimeters high, and they can flex by inclining their angle to the inside or outside, as rubber does. And so the fixed point was virtually in the bridge center. By temperature increase, the beam lengthens, and the bearings stand inclined to the outside and the other way around. So uniform distribution of longitudinal loads via these rubber bearings onto both towers. On the other hand, somehow we have to prevent that the bridge runs away. So we used here, that's a plan section. That's the tower, that's the beam, and here's a vertical elevation. So we had bumpers. We had here some 10 centimeters play, but the bridge could not run away because it was stopped by these corbels. And in transverse direction, we also had bumpers, so wind transversely buffeting or so, the bridge would bump against the tower there. We are rather slender. We have a 381 meter span with about 1.8 something meters depth, which gives us 1 in 200 slenderness for the beam. And it's an open section, not a box, so it's a rather wobbly. And this shows up in the increase of moments due to life load, due to nonlinear theory or P delta effects, as we say. There is no proper translation for theory of second order. You cannot say that in English, it's not known. So I use the word nonlinear effects. So we have an increase under life load in the range of up to 15-20%, and in the ultimate limit state up to 25% due to nonlinear P delta effects. It is a rather slender construction. Now, we come to the construction. The towers, I told you, form a truss in transverse direction. Wind from the cables and from the beam acting here goes down in tension and compression. That permitted to narrow down the width of the towers to 7 feet. Well, the thing is, of course, calculated and designed in feet and inches, and we've translated it here, but these 2.13 meters are actually 7 feet. And up for the, about 140 meters up the tower height, it's rather slender, but we needed to save some material to beat Jean Muller. So that's an absolute minimum possible because of the truss action. Longitudinal direction, we need more widths. Already for free cantilevering construction, it acts as a cantilever, it needs some stiffness. Then we are in the Houston area. It's alluvial soils, which means sort of very fine clay and so, which came in with the water, mud, better mud. And the rock is down some 300-400 meters, no way to reach it. So we decided on what we called a floating foundation. We used square concrete piles, 50 by 50 centimeters, post-tangent, and they were hammered into this alluvial soil, and in a way they were floating there. Naturally, you need a criteria how much you can put on, and that has to do with the settlement, how much settlement do you permit. And we could load the thing with 200 tons each, and that then gave this type of foundation. We have here an advantage of the lighter steel composite deck against the heavier concrete deck. With bad foundation conditions, a lighter beam pays in savings in the foundation. So that was one advantage here. It goes on then, heavy reinforcement, 40 millimeters, which I personally don't like very much. The end connections are questionable, but that's the way you do it in the US. And then we had more than 1,000 cubic meters of concrete per pile cap, cast, of course, in one go, 24 hours a day, and that gave us this nice photography. Now, after the foundations, we start with building the tower legs. And we had originally proposed to the contractor to use individual jumping forms for each leg, but the contractor started with one very big, heavy truss across with 2 cranes running on top. Very heavy equipment. It worked, but it was difficult to change the thing up to the next position and so on. So for the next 2 legs, they then used individual forms. Here is the first tower, and here they had already, you see it here, small individual forms for each of the tower legs. Of course, we need transverse ties or struts to take up the inclination, to take up the moments. And here then, at the top, they again used the truss to reach along both half towers. Here we see the struts temporary to take up the inclination, and here then the casting of the tower heads with the cable anchorages in started. Just to give you an idea that we were really squeezing the thing, we had 2.1 meter wide tower legs, 30.5 centimeters thick, which of course is 1 foot. And then we had two horizontal and vertical reinforcement inside and outside. So we had in the 30 centimeter thick walls 4 layers of reinforcement, 25 millimeter diameter. So it was rather a little bit tight, but it worked. And the real problem, of course, was where in the middle the two tower legs cross one another. And there we really had some tight reinforcement. But it was the cage, the reinforcement cage, 200 tons weight or something, was prefabricated on ground and lifted up in place, and then we used special graded aggregate, not the usual 0 to 32 millimeters, but 0 to 16 millimeters, special design, plus super plasticizers, which makes the concrete really good flowing, and it worked. It was possible to cast this part in a good way, and when we took away the forms, no honeycombing, you know, the aggregate showing up, it looked very nice. So it was just possible. Now, the tower heads. Again, you know that we, in concrete, cast in a steel pipe on which then the anchor head rests. And as already explained at the Helgeland Bridge, to take the horizontal components, we use loop tendons this way and that way to tie together the two stay cables. I've explained that to you at the Helgeland Bridge already. It worked there, so why not use a good thing again? And here we see how the casting of this tower head, which is also a little bit involved, was done. We always insist of preparing all the forms with the critical geometry of the steel pipes on ground. And we see it here. These are the inner forms from timber, and here are the first very steep steel pipes. And then, of course, around that is an outer form and cast into concrete. In the next step, the reinforcement is placed here around the steel pipe. You can see it here. And here you just see one of the loop tendons, I told you, which tie together. Now, then this is lifted up by tower crane, placed onto the form the similar way below. And so we guarantee that we have the exact geometric correct position of the cable anchorages. Not just sliding forms and let's see, bang it in there, and then we end up somewhere 10 centimeters left or right. I've seen it, not with my bridges, but one has to be very careful there. Of course, jumping forms, not sliding where you are under pressure time-wise, place it and all that. This is the completed tower head. We see here how the steel pipes come out, and these are the anchorages of the loop tendons. Now, beam construction. As I showed you, we have two separate beams and open plate girders, a web, a bottom flange, and a top flange. These are all some strange measurements, but that's 6 feet here, and then comes another foot. That's how these strange millimeters come, because we have converted it. We have then, this is welded in shop, the stiffener here, but the connection to the cross girder is done on site, so it's bolted, cover plates and high strength bolts. And then we have here some cast in place roadway deck, plus we will see later precast elements for the roadway. But that's the heart of the matter, and it's not very strong and solid. Remember, we had 25% increase due to due to nonlinear effects. It is a little bit wobbly, the whole thing. But minimizing cost, winning the game, that's what we were after. Now, fabrication of the steel was an interesting story. At that time, and still today, there was in the US a so-called Buy American clause. That meant you had to buy the steel from US sources. And that would have been more expensive than if you had bought it and fabricated it outside. And so we were fighting politically to get this ban lifted, because the concrete wasn't suffering under that, the concrete alternate than we. And well, for the good taxpayers in Texas, we saved a little. We saved some money, and we got the Buy American clause lifted. And so in the end, the steel was fabricated in South Africa, coming from South Africa itself. And you see here a lot of black people. It's in South Africa, in Cape Town. May have been an important factor that the steel alternate won. You know, it's not always the QL squared eighths which assure you the job. And the state of Texas highway department went there, our people partly to supervise the construction, and so they had a nice trip down there on taxpayers' cost. Everybody was happy. Here then, after fabrication and first primer in South Africa, the steel parts, main girders, cross girders, were transported by ship to site, and then pre-assembled, test-fitted in the pre-assembly yard. And from there, the beam construction started. We had separated the steel grid and the concrete deck. So 60-ton lifting weights for the steel grid was the maximum we had. It started just with the tower crane lifting up the first piece of beam. After that was in the lifting derricks were installed on the beam. We used these derricks for lifting all the material which came on by water and lifted up. You know, we could also transport it on the beam. We could use floating cranes. This was the decision the contractor made. Now, to install the beam, free cantilevering piece by piece, we see here just a little bit, there's the water of the Houston Ship Channel, and the steel grid pieces in, again, the length of a cable distance. There was always one pair of cables attached to every steel piece. That's quite usual, something like 12 meters. So, steel piece was lifted, spreader beam here, 60 tons was the highest weight, and it was connected, the new one, to the already installed beam. We see here the Houston Ship Channel. The ship is just leaving. And as I told you, no side welding in the US. We do it the good old way, cover plates and high strength bolts. And strong men standing up there 50 meter high with a wrench and pulling it together. It's hard for you to find something in Germany, it's all welded, but there it's the method of choice. And the steel workers have a strong part of those people on site. I took all these pictures myself. I was on site quite often, and I was impressed how well and they worked. I mean, that was their daily work in Germany. Up 50 meters, I think people would make more ado about the danger of falling down. I mean, they had some ropes, safety ropes and things, but they were outstanding people. Now, after the steel grid is installed, we then transport the deck up with the same derricks. We had the basic consideration to do we want cast in place or do we want precast? And we had offered both in our tender documents, but the contractor decided he wanted to do it, as you say on site, piecemeal in small pieces, and then accept the joints, which are of course the shortcoming. On the other hand, shrinkage and creep is less. So this is a good method. We see here the precast plate piece by piece being lifted up, resting on the top flange of the cross girders, and we see here the top flange of the cross girder. We didn't need any more form. That was all. There was no additional form for the cast in place joints. And in order to avoid many cracks in this region, which can take place if you just use loop splices, we extended the top joint so that we could have here straight lap splices, and only underneath, where we had to come to be close enough to be on top of the cross girder, we used loop splices. If we have some cracking here concentrated, it's of no importance. This worked very nice. We see here the joint, the straight lap splices on top. We see here the shear studs protruding from the top flange of the cross girder, and then it's cast with special mixed concrete, small aggregate, 0 to 16, super plasticizer, low shrink, and so we did not have crack problems in these joints. Of course, due to the inclination of the stay cables, we have the beam under compression all the time, which naturally helps a lot. But even later, if we have under live load or so a little tension, cracking was not serious. Now, free cantilevering was started, went on. See here, typical tanker coming from the Gulf of Mexico into Houston Harbor. And remember the hurricanes. Now, we had a very thorough aerodynamic investigation. Professor Robert Scanlon, one of the top aerodynamic people in the world, was here in charge. He died 3 or 4 years ago. Outstanding man. And we found we need some tie downs in case the hurricane hits us during free cantilevering, when the bridge is most vulnerable. And so we see here tie downs to the tower foundation. Eccentric it has to be, so there were some additional piles, and in transverse direction it's inclined against torsional. And with this, it worked. We had at least 2 hurricanes during construction going straight over during the 3 years. And the bridge behaved exactly as expected, as calculated. The cantilevers made 1.5 meters plus minus movement when we were really far out. And everything worked fine. Here we have then the situation that we have free cantilevered the two, and we are ready to close the side span joint. I may add that, of course, it was a decision, shall we first build the first bridge complete and then the second beam? But one reason why we built it in parallel was that aerodynamic investigation, especially wind tunnel testing, showed that when we have two beams side by side, the two beams are more stable than any single beam, which has to do that there is some energy transfer from the forward to the backward beam, which disseminates energy, and so it was aerodynamically safer to build the two, although unconnected beams, than to build one single, and the hurricane was a problem there. So, and in addition, the contractor said, well, that helps, makes material transportation easier and all that. That's why the two beams were built in parallel. Now, we come to the side span joint closure. There at the side span, we have the backstays. You know from our calculation examples that the bridge hangs into the backstays. All the center span loads are carried back by the backstays to the foundations. Therefore, we needed 3 stay cables as backstays instead of 1. And now these we could only reasonably anchor in a box. Otherwise, we had an open cross-section where we bolted some box on, we'll see later. So we have then at the end widened the plate girder to a box where the backstay, very strong backstay cables are anchored. It's connected to the pier here with a pin, and it's cantilevering out here. And because that's only, here we haven't done, 1 foot 9 inches. Well, how much is that? Roughly speaking, 40 centimeters wide, and it would be very difficult to inspect. So it was closed with concrete. Once it was all done, concrete was poured, low shrink and all that. So if you can't inspect it, you don't have to inspect it. And we see here lifting the end piece of the beam with 1 cross girder only, and then connecting the cantilever. We see here the piece with the 3 backstay cables I explained to you, and here where it is connected, this piece at the end then to the hold down pier. Now, side span joint closures have been done. All what is left is the center joint closure. As always, it had to be surveyed very carefully because the last piece has to fit. And very often one surveys and then fabricates the last piece, the closure piece, a little bit longer to be able to cut off in a little skew or so that the thing fits. So you have to survey very carefully, and you do that always very early in the morning, just before sunrise. Because then, especially in Texas with the hot sun, the non-uniform distribution of temperature from the sun hot on the deck, is even out as good as possible. And so this is in the morning just before sunrise. And here we lift up, flying the flag, of course the Texan flag, the last piece. The 2 beam halves were moved back at the towers. You remember we had there these corbels, some joints. Put a check in there, pushed outside. So the piece, the whole half beam, moved to the outside. The bearings were a little skew, and the hold down piers were flexible enough also to the outside, everything to the outside. Then we have enough space getting in the last piece and then taking back the jack at the corbels, at the towers, fits in, cover plates, high strength bolt, done. So stay cables were a little special. I mean, the design was in the early 80s, and it was a mixture between shop fabricated and fabricated on site. First of all, strand cables. And this is a typical strand cable. You see here the cross section, but it was still cement grouted, which we later did not do anymore. And here the anchorage with the wedges, you know all about it. And it was then prefabricated on the approach deck, but the whole cables were prefabricated here, not in place, shifting in one after the other, which we will later see. Our shop, so to say, was the approach bridge. We had them all shop fabricated here. You see here inserting the strands into the wedge anchorages. And then we used a high line over here with hangers and rollers to transport the completely prefabricated cables on the approach bridge to the main bridge. And then came the usual, now we have the installation of a shop fabricated cable, complete cable with some lifting it up. Now at the beam we had a box anchorage bolted to the web. The requirement of the Texas Highway Department was they wanted not only the cables exchangeable, but also the cable anchorage, saying something can go wrong. And so we had to bolt that, and then we had to put it on here, and then for stressing here, the bottom flange was in the way for the tension rod, for the tie rod, what I told you. So we couldn't stress at the beam, but we stressed at the tower, possible, but you need to have the space. The tower head was a little bit bigger than normal. Anyway, the bottom end was introduced here, secured with crossbars, and here we see this box welded, and here's the anchor head already, and now we cannot stress here. The bottom flange of the main girder is in the way. We stress in the tower head, so we introduce it in the correct angle, everything as you know, and here we see we introduce it through the steel pipe. We have then here the jack chair, and we have the jack for the big jack for the complete cable. And this space we spent quite some time to be able to get the jack and the jack chair in up there. Normally, we don't have that in the tower head, but it was designed that it worked. And here we see the rather sizable jack for taking the strands which protrude and stress them. I've shown you that in general a few lectures ago. Cables are in, they are cement grouted. Cement grout I showed you for the Pesco-Kennewick Bridge, how that works. And then, of course, many say black is beautiful, but sometimes with stay cables people say, no, we'd rather not have the black PE pipes, we want a color. We cannot paint because PE is chemically inert. Paint does not stick on PE, it flakes off. So the only way we found was to use tape, sticky tape, 50% overlap, so it sticks on itself, it's glued to itself, and that seems to help. Then we need only to find a tape which is UV resistant. PVC is not, as we found out, but we found PVF tape, polyvinyl fluoride, which is UV resistant, nicely colored, brand name Tadler, and that's what we used and had lots of tests done. So we wrap the cable, and then we sink against the dark blue sky and the intense sun in Texas. That looks very nicely. So the completed bridge, bird's eye view. Here we see the whole thing. We have here the typical problem that for stay cables which run together at the tower, fan arrangement, and here we have even 4 cable planes, that in a skew view they visually intersect. Not too nice. But then we say, okay, if we have so many, we say it's more the impression of a veil. What's a veil in German? What you have in front of your head. It's the impression of a veil, and it's not so disturbing. That's a longitudinal view. That, by the way, was on the cover of the German magazine Stahlbau. When we had published the bridge, they chose this as their cover photography. And this is a picture I took at night, floodlighting the bridge. And of course, finally, sunset in the Gulf of Mexico. There are spectacular sunsets in summer when there's rain around. Well, to sum it up, we looked into composite cable-stayed bridge. The main thing is that the beam consists of a steel grid with a concrete deck, and it's helpful for construction that we can install it in smaller units. Typically, we have the steel grid over the full width, say 20 meters of a bridge, and in a length equal to the cable distance, say 12 meters, so that we have one pair of stay cables for each new beam section. We lift the beam section, range of 60 tons, smaller weights compared to 300 tons I showed you in precast concrete elements. We can use cast in place concrete deck. The advantage is we can do it in one go. On the other hand, we have then to use formwork for the deck, and we have high shrinkage and creep. The alternate, which I found is more economic, is to use a deck from precast slabs resting on the cross girders, cast in place joint, which are certain disadvantages, but because of the compression from the natural compression from the stay cables, they are under compression virtually all the time. So the weak spot, which joints are, they are weak spots. It can easily or good overcome if you have a proper design of the lapping, you have a good concrete mix, and you cast it carefully. So this is the heart of composite cable-stayed bridge construction. By the way, we won hands down against Jean Muller's concrete alternate, and we had ours back. Thank you.